Okay, assalamualaikum and good morning. So sorry for being late. Just out of time preparing notes. So probably today we might not have a 2-hour lecture, but probably shorter than that. So let's look at the notes that I prepared so far. Yeah, I have not uploaded this on Putra Plus as yet. Just finished it this morning. So today we are looking back. I think we have started this a little bit, this lecture. So we are looking at the case of the second law in the context of the one that you're probably more familiar with, which is that entropy is always increasing. And this we have already started before by comparing, for example, the case of the efficiency of your Carnot engine with another heat engine, which is going to be an irreversible one. So you'll find that the Carnot engine is the most efficient. So essentially you have this from the definition of your before this. So the only difference that we did was to change the convention heat release by putting a negative sign on top. Okay. And then the other thing for the reversible case, we also know that that defines the absolute temperatures. So this is given in terms of Q2 over Q1 with the negative sign, of course. And then this is equivalent to T2 over T1. And this is for the Carnot cycle thing, okay? But for irreversible processes, we know that this is going to be following this inequality. So in other words, if you check back, no, there's a reverse sign as well. So you'll find that, okay, for the context of the ratio of your heat in your irreversible engine, it will be greater than the absolute temperatures, the ratio of the absolute temperatures. Okay. So we have done that, or I'm just going through again. So one can consider small, what you call changes of the heat. Okay, so you just consider the it's not the exact differential, but it's a small differential which is not exact. Okay, rearrange this particular inequality to give this particular form. Okay, so in other words, what one would have, this is essentially good for small irreversible cycles. Okay, but you can sum all these small irreversible cycle to give a general irreversible cycle, for which you have an integral over a loop, okay, over a cycle, and that should be less than 0. Okay, so this is again trying to type too fast, and T is the temperature of the bath supplying the heat. Okay, and then I think we have also done this. We make the cycle to be composed by two different paths. One of the path is going to be reversible. Okay, so the top one is reversible, and the bottom one will be irreversible. And then the composite thing, okay, the whole thing, this cycle, so to speak, is actually an irreversible cycle, because part of it is actually irreversible. So in other words, definitely the whole thing as a whole will be irreversible. So in other words, this will apply, okay, and then one can essentially, again, I think I've done this as well. So one can write this as BADQ T plus B, sorry, A, B, dqt, where one of them is going to be the reversible one. So probably this is the reversible one, and this will be the irreversible one. Okay. And then that has to be less than 0, and then you rearrange it, and then you change the integral limits. Hello? Yeah? Okay. Okay. So okay, can you hear me, guys? Okay, just give me a minute. So I've changed my Wi-Fi to broadband instead. Okay, I should be back now. So where precisely did I stop? Got disconnected. I've done this, right? Can somebody help me here? Anyone? What's going on here? Are you, am I still with you or what?
See the slide again.
Okay. So I think,
A little bit up.
okay. Yeah?
Yeah.
Okay.
For reversible process, you explain the beginning of the process, then you get it stopped.
Okay. So I will just go through this quickly because it was already in the previous lecture. So as I said, we are looking at the efficiency of the reversible engine and the irreversible one. Okay. So for the reversible case, you have an equality, but for the irreversible case, you get this inequality. Okay. So remember your T1 and T2 are just essentially your temperatures, absolute temperatures defined through Carnot cycle. Okay. So in other words, over here is the ratio of your heat input and output, or well, input is the one underneath and output is the one on top, is related to the absolute temperature through the inequality rather than equality. Okay. So the idea is now, if you look at the case of small irreversible cycles, you can compose them just like case of the reversible ones. Then you can actually say, for the case of irreversible cycle, then you have this inequality of over the irreversible cycle, that this heat taken in over the temperature T will be less than 0. Okay. So, and what we want to do is to rewrite the cycle in terms of a more specific what you call path here over here, where one of the path is actually reversible and the other path is actually irreversible. So you just compose these two. So essentially the idea is now you can impose this inequality that works for the irreversible cycle as a whole. Okay, but now you are able to put the limits on it. Okay, So you essentially you have your reversible part going from A to B, and then for the irreversible part, go from B to A, and then that will give you the cycle with the inequality sign. But now one can sort of rearrange this equation, okay, so that you get the case of the irreversible path is less than the one with the reversible path. And the reversible path, you already have seen that you can write this as a state function of the entropy. Okay, so that is the second line in this particular equation. So entropy over here only defined is because it's a state function. It's only defined by the endpoints over here. So one can make these endpoints very close to each other, so that no, your B is just A plus delta A, for example. Then one can apply the infinitesimal version of this equation, which is written in this way. And this is essentially what is called the Clausius inequality. Okay? And one considers the system that we are looking at to be thermally isolated. Okay? So in other words, you consider that there is no input from the surroundings of that system. So in that particular case, then you have your delta Q to be equal to 0, and essentially that gives you 0 over here. So you get 0 less than delta S, or delta S will be greater than 0. And remember that this is change in entropy for the case of a thermally isolated system. Okay, so this is what essentially is called the law of increase of entropy, which is the second law, the common what you call the common statement of second law that you already seen before. Okay, and one has to remember that this is only true for the case of a thermally isolated system. So as a consequence of this particular mathematical statement, really, one would actually find that, okay, if a thermally isolated system is going to reach equilibrium, then one would expect that the final state after reaching the equilibrium should have the maximum entropy. Okay, why? Because in that sense, you can no longer make changes to the system. Okay, otherwise you can always increase the entropy, but since when you reach equilibrium, there should be no more changes. Okay, and then when there's no more changes, that means you have reached your sorry, what am I doing? Your S changes to S max, so that no more, if there are any other changes that comes from what you call the system reaching the maximum entropy, it can only becomes delta S equals 0. Okay, so in that way, then you don't have any more changes. Then essentially the equilibrium state is a state of maximal entropy for that particular system. And this is also related to the case of the idea of heat can only flow from a hotter body to a colder body. Okay, so if you know, for example, when you have the hotter body in contact with the colder body, then there will be heat flowing out from the hotter body until it reaches equilibrium. And we will look at this again in a quantitative way. And then you'll find that, okay, once it has this equilibrium state, there will be no more heat flow going from the hotter body, or in this case, the bodies, the two bodies already reach a thermal equilibrium. That means they are having the same temperature. Okay. One of the things that has been also speculated about this increase in entropy, you see that it's like a one-way nature of this law, and this one-way nature is somehow associated with a preferred direction of time. So, for example, later on we see the case of a gas expands. It will never go back to the original once it's expanded, because that expansion is an irreversible process. It will no longer go back to the case of where it has the original volume. Okay, so in that sense, you see that the expansion of the gas seems to tell you also, it's related to how the system evolved with time. So in that sense, that is how it gets how it gets related to one another. Okay, because you only sense the changes, okay, in the system through the evolution of time. It is in no way explain why we have this preferred error of time. Okay, has been a philosophical debate. There are a lot of debates about this, but no, I'm not going to go into it. No, we can look at some papers later on as part of your student-centered learning modules, so you can go through some of the papers there. Okay. So the next thing we want to do is to see how we can apply this law of increase in entropy to certain examples. This is all of these are actually is in the book. I've tried not to get way too much from that book. Okay, so I'm just more or less putting it in a better, not to say better form, but in a note form, so that you are able to read it easier than just reading the book. Okay. So here there are three examples that we're going to look at, and these three examples come from three irreversible processes. Okay, one is with respect to the two thermal bodies in contact with each other. The other one will be a mechanical case, which is a spring and a mass. And then the other one would be with respect to the expansion of gas. Okay, so we look at how we can actually calculate the change in entropy for those systems. Okay, so we look at the first case of the identical blocks. Okay, in this case, both of them having a constant heat capacity for simplicity. Okay, but these identical blocks will have, one of them will be at a different temperature. Here is 320 K, and then you can have another 280 K, and then after that, we put them in contact with each other. So in other words, as you probably would know, that the hotter body will lose heat to the colder body. Okay, and one could actually calculate the total internal energy of the system by just multiplying your heat capacity, which is supposedly given over here, okay, multiplied by the temperature T. Okay, so the final system would be somehow, it has to be here you have one block to be at 320, the other block would be 280. So it will try to thermalize and be in equilibrium with each other, so that it becomes the same temperature. So you can calculate that to be 300 K. So here you can see that, okay, this is going to lose, it's going to drop temperature about 20 K, and this will increase by 20 K. Okay, so one can actually calculate the entropy change for each of the blocks. Okay, for the hotter one, okay, we know that, okay, we have CV dt over T for the change in entropy. This is coming from a previous lecture, I think, if I'm not mistaken. Okay, so then you can integrate this part. CV is just a constant here, and then you can integrate this dt over dt over t, but you have to remember what are the limits over here. Here the limits for the hotter block is 320 K as the initial temperature, and then the final temperature is 300 K. Okay, so one does that, put that into the limit. Here basically you get a log, and here you have a smaller number above and then bigger number below. That will be a a negative. When it comes to taking log, it will be a negative quantity. Okay, so what about the colder body? Then you do the same. So here again the limits are different now. It's 280 goes into the final temperature 300. Okay, and in this particular case you can see that the numerator is actually bigger than the denominator, so that will be a positive number. So one loses the negative change in entropy, one is a positive change in entropy. But the combined system is not going to give you a zero thing because it's an irreversible process. So when you combine these two changes, you'll find that, okay, when you calculate that, you get this CV is a common factor there, and then you have a log plus a log, and you know what that means. There's just a multiplication there. So you have your 300 times 300 divided by 320 times 280, and you can calculate that, and essentially that gives you this quantity. Okay, so there is this non-zero change in entropy in this irreversible process. Here is the case. Probably it's a bit, simplistic over here. Here essentially you think of this whole system of spring and mass. Okay, the mass was put onto this spring. Initially, the spring is unextended. When you put a mass on it, and it gets extended by some amount here, for example. Where's my cursor here? So there will be an extension due to this weight of the mass. Okay. So there will be, so how do we calculate in this particular case is, remember this is unlike the one above where one looks for, say, the internal energy, for example, given by this heat capacity times the temperature. Here there is none such, over here, what makes the thing different is because of the mechanical processes that is involved. Okay, so one would actually look at the potential energy of the spring, given that it's going to be extended. So from normal classical mechanics, you know that the potential energy of the spring is given by half kx squared. K is your spring constant, and then simultaneously, besides the spring, you also have the mass sort of lowers down in height. Okay, so so it has this different gravitational potential energy. Okay, due to this extension. Okay, so the total potential in this particular case is just like your internal energy in this in the previous example. The total potential is given by half kx squared minus mgx, and if you remember how this system is going to behave, since you have initially an unextended spring, and then you put a mass on it, okay, the spring gets extended, but then you have your spring constant, sorry, your what do you call that? The force that sort of reverse the extension of the spring. So it tends to move back and forth, so it will oscillate, and then finally at some point it will come to rest. And when it comes to rest, that point from the oscillation to the uh, rest position of the mass is actually an irreversible process. So one should be able to calculate what would be the entropy change due to this irreversible process. Okay, so in other words, over here it will have to come from this potential energy of the system given by the spring and the gravitational pull. Okay, and you know that when does it come to rest is when it reaches mechanical equilibrium. Okay, and mechanical equilibrium occurs when your dv dx equals to 0, giving the minimum v, and you can essentially calculate what is the position of the mass at the equilibrium state, which is given by that. Okay, so when it comes to the rest and it has this particular position xe here, then one can just simply write this what I call the spring energy constant. Okay, actually, okay, the, the potential energy of the spring. Okay, with respect to the extension through the mass, which has now reaches equilibrium because it also there's another force acting on it. Okay, which is through the gravitational pull. But now it comes to the rest, and then it has this particular potential energy value. Oops, my thing has gone. I'm having problems with them now. Give me a minute. Okay, never mind. I'll just carry on with the keyboard. Okay, the other case which I already mentioned a little bit before this is the expansion of gas, and you know that when the gas expand, it is by observation that you know that you can go back to the original volume. Okay, so here we can consider what. So that will be an irreversible process. So there will be entropy change. So how do you calculate the entropy change for this expansion of gas? Hopefully my tab is still not working. Okay, anyway, so let's consider the case of a gas with some volume V placed next to an empty vessel of the same volume. So, and then you allow the gas to enter the empty vessel and then occupies the empty vessel, so that the total volume now becomes sorry about this, my tab is not working. Okay, never mind. I suppose I have to do the cursor. So the final volume, would be 2V instead of the original V, and you know that this process is irreversible. So how do you calculate the entropy change? Well, in this particular case, we assume that the gas that you're looking at is an ideal gas, and you already have a formula for your entropy there. So which is that, okay? And then the other thing that one needs to see over here, there are two different parameters or two different thermodynamical variables, your theta here and V, but where one can actually do an experiment for which the gas expansion doesn't bring any change in temperature. This is the experiment by Joel, So when that happens, this part will not contribute. The only part that contributes is this particular part. Okay, so one can actually see now if you do the changes over here from the original volume of V to 2V, it will be that, and that will give you the entropy change under the gas expansion. Okay, never mind. Right, the last final part of this book, or this chapter of this book, is to see how one gets a few conclusions that one can take from this law of increase of entropy. So let's consider the case of two systems not in thermodynamic equilibrium in the beginning, okay, and then you allow it to be in thermal contact. I'm a bit frustrated with my tab now. Okay, never mind. So the total energy of the system now is given by the internal energy of A and internal energy of B, and we assume there is no, this is thermally isolated, this combined system is thermally isolated, so there will be no loss of energy, so this will be kept constant. Okay, but between the system A and system B, you allow this to change energy. So the energy can pass from system A to system B, for example. Then one could write your entropy of the total system as follows. I wish I can write on this, but let's check again. I'm not sure what's happening with my tab. So, okay, anyway, so over here, what is being written over here is the total entropy here. S is your total entropy, okay? And then SA will be entropy with respect to the system A, and SB will be entropy with respect to system B. The one in the bracket is essentially like a variable. So S as a function of UA, and why is that done this way, so that essentially you allow, since this is going to be kept constant, I can rewrite your UB, okay, the internal energy of B over here, to be just the total U, which is a constant, minus UA. So now the whole thing essentially expressible in terms of a function of UA. So that's essentially the idea. So as if you want to what you call see how the processes changes after time, then we can use the Clausius principle again, or the law of increasing entropy, so that the derivative of the entropy over here will have to be with respect to time will have to be greater than zero, okay, because your entropy is always increasing. Okay, so in that particular case, I can now differentiate this equation over here, okay, and then I can re-express the, remember that the equation is the differentiation is with respect to time, but I'm already specifying my entropy as a function of UA. So I use a chain rule. So I have the time derivative of UA with respect to the time derivative of UA, and then you take the derivative of the entropy of A with respect to UA, and similarly for this is supposed to be SB, sorry, again I cannot change it here because My pen is not working. Now this is SB, UB over here, and then you use the fact that, okay, I would need to know how UB changed with respect to time as well, but UB changed with respect to time is just negative of UA change with respect to time, because you have the total internal energy to be constant, and then you basically have this to be equal to 0, and then you can get this quality, and you can substitute now this into the equation above, and you can see that this is essentially this is SB, which is corrected down below here. Okay, so you have this, and one of the things that we need to do is to remember some of the derivatives that you have seen before. When you use when we learn about free energies, we have some first order derivative with respect to some variable over here. Here is actually equivalent to the inverse temperature. So you can look it up, I think from the last lecture, if I'm not mistaken. So this is 1 over temperature, and this is 1 over temperature of the other subsystem. Okay, so this together with the law of increasing entropy here, would have this equation there. Okay, so if the system is in thermal equilibrium, that means there will be no longer entropy changes. So this means I have to have your TA and TB to be equal. Once T8 and TB to be equal, then this thing becomes 0, then S becomes a constant, and the system will be in the thermal equilibrium. But if it's not, for example, at the beginning of the process, you might have the temperature of A greater than temperature of B. What would happen in order to satisfy this greater than equal 0 thing? Temperature of A greater than B, this will be smaller because this TA is bigger. Are you seeing my cursor? By the way, I'm using my cursor to point where the terms are. Can somebody give me some feedback, please? Okay, great. So you can see that this TA is bigger, so that means 1 over TA is smaller, and 1 over TB is bigger. So this will be negative, but then you want this to be positive. So in other words, the only way that this can be positive is to make dUA dt to be negative. Okay, so you have that as a conclusion. So that would actually says what? Okay, that will say that, okay, that the energy will leave system A, or in other words, the hotter system. Remember that T is bigger than TB. The hotter system loses energy to the colder one. Okay. Now, that's done for the case of thermal equilibrium. Remember that we have many different types of equilibrium that we have seen before. So let's introduce the others. So in this particular case, we want to introduce, for example, mechanical equilibrium. So one considers that there's a piston that changes the volumes of the subsystem A and B. So again, then over here we treat the volume of one particular subsystem as the variable. The volume is the total volume is intact. Okay, it doesn't change the total volume, but no, the individual volumes can change because of the piston. Okay, so we can write this as that, and then we again calculate the rate of change of entropy. Okay, so in this particular case, you take the time derivative of the variable that's appearing here, which is VA, and then you do the chain rule thing, and then you get this partial SA over partial VA minus with a partial SB over partial VB. And again, if you look again some of the first order derivatives that we have seen with respect to the thermodynamic variables before, this correspond to the ratio of your pressure with respect your pressure over the temperature. Okay, so you have that, and that has to be greater than equal to 0. So let's look at the case of the mechanical equilibrium first. First of all, there are two things over here. There's a P and T. So one has to assume that, okay, to make the system, no, to make it a bit easier to analyze, we consider that the whole system is already in thermal equilibrium. It's just a mechanical equilibrium that we are concerned with. So in other words, TA equals to TB. So the only way that this thing can be equals to 0, or no, S is constant, is to make PA equals to PB. Okay? And then that once that is done, then your system is in what we call mechanical equilibrium. So what about before that? Well, one of it could be, say, the pressure of subsystem A might be bigger than pressure of subsystem B. Then in this particular case, if we look at the equation, we need this to be positive. So the only way that can be positive with PA greater than PB, so this is also positive, then we need this to be positive. Okay? So that means dVA dt is going to be greater than 0. So in other words, the subsystem A, which has the higher pressure, will actually expand. Okay? So that is essentially a processes going from, say, what you call a state which is not in equilibrium going to the state of equilibrium. Okay. The one that we have seen is the thermal case, thermal equilibrium, and then we have seen the mechanical equilibrium. There is one last equilibrium that one should cover, is the fact of that the number of particles in the subsystem can also change. Okay, so in this particular case, we consider the number of particles in system A, which is given by Na, and then the particles number of particles in system B, which is given by Nb, and these two numbers can vary, but the total number, okay, the total number of particles will stay conserved or will stay constant. And again, like before, we express the entropy as a function of this the number of particles over here. So we choose A again. So you have S as function of Na equals to entropy of subsystem A as a function of Na, and entropy of subsystem B as a function of Na again. Okay, so again, we do the differentiation with respect to time to see how this thing evolved. Okay, and then you find that, okay, you have this chain rule again applying here. So that means you differentiate Na with respect to T, and then you look at the changes of the entropy with respect to the particle number. Over here, this has previously we have not covered this changes in terms of number of particles. So we need to introduce something just like the case of the other variables. So we define a chemical potential, which is written as the temperature times the partial derivative of the entropy with respect to the number of particles. Okay, and that is called the chemical potential. And when you do that for each subsystem, so in this particular case, for example, over here, I would have multiplied by the temperature, of course, I would have the case of mu A, okay, and then the minus sign is already taken out front, and then here will be mu B. Okay, so you have that. something going on? Please shout if something happens. So, so in other words, so here, if you want to have the system to be in equilibrium with respect to the changes in the number of particles, then one would really need to have the chemical potential to be equal. Okay, we are assuming again the whole system is in thermal equilibrium, so that means your temperature is the same here. So that requires mu A equals to mu B, so that the SDT equals 0. If for some reason your chemical potential is bigger than one subsystem than the other subsystem, like mu A is greater than mu B, then again the imposition of this to be greater than 0 being positive here, and remember there's a negative sign over here, okay, and mu A greater than mu B, this is positive, okay. So the only thing that one can make it positive, the whole thing, is to make this thing negative. Okay, so when you take this to be negative, so given that, so that means this is negative, meaning it loses the number of particles there. So a system with higher chemical potential then is it going to lose the number of particles to reach the chemical equilibrium. And that is precisely, I think, that's where my note ends. There are a few more things I wanted to add. I didn't have time to do this morning. So let me go, if I can have my, let's see if I can use my whiteboard just to end the thing. Okay, just give me a minute because these programs tend to be slow in loading up. No? Okay, it's coming. Hopefully I can write on it. Okay, this is going to take some time. Oh dear. Can I just do this without signing in? I can't remember my own password now. Okay, let's see, I can do it. Something went wrong, try again. Continue. I hope it doesn't prompt for my password. I have to look it up. Okay, this is taking too much time. So let me go to the book itself. I think the last part of the book. Can you see the book now? Okay. So it's just I'm just want to finish off the last part, which is when we did all this calculation with respect to the entropy, taking the derivative with respect to time, we are assuming the entropy as a function of a single variable. Okay, one could have actually make it, a function of several variables, and then the differential of the entropy is now given in terms of the various variables of the function, the variables that the entropy depends on. Okay, so in this particular case, you have your u, v, and n. So you have partial s, partial u, du, partial s, partial v, dv, partial s, partial n, dn. And one can refer back that this is related to the reciprocal of the temperature times du, and then this one will be the one with respect to the pressure and over temperature, and finally this one will be the chemical potential thing divided by temperature. So this whole thing will if you don't do this separately, you will always have to consider all these changes with respect to the different variables inside your entropy function. Okay. The other thing is probably the analogy of the mechanical work. For the mechanical work, we know that P times V is the mechanical work. So here one can also think about mu times dn, or here P dV. Mu times dn can be thought of as a chemical work. Okay, so I think that's probably that finishes up this. I think it's chapter 2, right? Chapter 2 of the book. We are supposed to go into the next chapter, okay, which is just a revision on probability and statistics, which for today I've not prepared anything on this. Now I've read the book a little bit, but don't have any scribbles on as a part of my notes. So I will have to leave this until the next lecture, probably next week. Okay. So there will be so since we have a bit of time left, so we'll have one assignment coming soon, hopefully by end of this week. Are you still with me? Okay. The assignment. Okay. Hopefully I get it out before, well by the end of this week, and then next week will be week 5. So probably you need some time to look over the assignment first, and then help you prepare for the first test, which I would suggest to be in the 6th week. And 6th week we have to do this on the Thursday, so that will be on the 25th. Okay. So your first test will be on the 25th of November. Okay. I hope that is fine with everyone.
Yes, doctor.
Okay. So I'll stop for now. Sorry for the short lecture today. It's just that I don't have too much time. I'm doing several different things. Okay. Thank you, everyone. So I will end the meeting now. Bye.
Doctor.